Hey there, welcome back to the deep dive. Today we're diving into something I think is really going to get those philosophical gears turning. We're talking quantum computing. And I know it can seem like this futuristic sci fi kind of thing, but it's really a fascinating blend of physics, math, and computer science. And it's quickly moving from just ideas to, well, reality. And I got to say, what really hooked me early on was the potential. I mean, you hear about things like Shor's algorithm, and it's like, whoa, this could change everything.
Absolutely. Shor's algorithm, it really shook things up, right?
Yeah.
The idea that you could factor these huge numbers exponentially faster than any classical method, well, that wasn't just some cool math trick. It raised these fundamental questions about what's even possible to compute, about the very limits of what we can know. And that's a goldmine for philosophers, right?
Yeah, exactly. And that's exactly what we're going to do today. We're going to explore the core of quantum computing, but through that philosophical lens. And to guide us, we're using the Stanford Encyclopedia of Philosophy's entry on quantum computing. It's really a fantastic resource.
It really is. It lays out this really great foundation, takes us through the history, unpacks the theory, and really highlights all these unanswered questions that are driving the field forward.
So, what's on the agenda for today? Well, we're going to start by laying out the groundwork, talking about computability and complexity. I mean, that's where it all begins, the very basis of what it means to compute. Then we'll tackle that big question. What makes quantum computation so potentially powerful? What's this quantum advantage all about? And finally, we're diving into the really deep philosophical questions. Questions about computability itself, about how we interpret quantum mechanics, and even about the philosophy of science. Sound good?
Sounds like a fascinating journey. I think with your background, you'll find this particularly intriguing.
All right, so let's start at the very beginning. Computability and complexity. And I guess we got to start with the Turing machine, right? That's the classic model, the blueprint for the computers we know and love.
Precisely. Alan Turing, back in the 1930s, he came up with this abstract model. It's basically a machine with this infinitely long tape, a head that can read and write on it, and a set of instructions. And what makes it so powerful is its universality. Turing showed that a single universal Turing machine could, in theory, simulate any other Turing machine. It's like a fundamental model for any process you can break down into a set of well-defined steps.
And then we have the Church-Turing thesis. If I'm understanding it right, it's basically saying what we think of as an effective method, something a human could do with a pen and paper given enough time, is captured by this Turing machine.
That's a great way to put it. The thesis basically states, if you can compute something using an effective method, you can also compute it using a Turing machine. Now, for a philosopher, the key here is realizing this isn't some theorem you can prove. It's a thesis, a very well-supported explanation of an informal concept. It's drawing a line in the sand about what we mean by computable in the most fundamental sense.
It's really getting at the very essence of what it means to calculate. But then, beyond just whether something can be computed, computer scientists got interested in how efficiently it can be done. That's where computational complexity comes in, right? And the distinction between tractable and intractable
We
problems.
got it. Computational complexity is all about looking at how much time and memory you need to solve a problem as the input gets bigger. Tractable problems are the ones you can solve in polynomial time. That means the resources needed only grow as a polynomial function of the input size. Intractable problems, though, they generally need exponential time, which means even with our best computers, they quickly become impossible to solve as the input gets even moderately big.
And all of this early thinking was based on the deterministic Turing machine, the DTM. That's where each step in the computation is completely determined. But then there were these other ideas, like the non-deterministic and probabilistic Turing machines.
Right. A non-deterministic Turing machine, NTM, it's kind of like exploring many different paths at the same time. It solves a problem if at least one of those paths leads to a solution. And a probabilistic Turing machine, PTM, that throws in randomness. The next step depends on a probability distribution.
And I guess the hope was that maybe these probabilistic approaches could be a game changer, that they could solve things much faster.
That was the initial thought. And for some problems, probabilistic algorithms did seem a lot more efficient. But the general consensus now is that PTMs don't really expand what kinds of problems we can solve efficiently compared to DTMs. And this is really key when we start talking about quantum computing, because it does seem to offer that kind of advantage, though proving it definitively is still a big challenge. So the real aha moment here for a philosopher is that we might need to rethink what we even mean by computationally feasible, thanks to quantum mechanics.
So to sum up, we have these complexity classes. P for the problem solvable in polynomial time on a DTM, NP for problems that can be checked in polynomial time on a DTM, but maybe not solved that quickly. Then there's BPP, bounded error, probabilistic polynomial time. Those are the problems that classical computers with randomness can solve efficiently. And finally, the big one, BQP, bounded error quantum polynomial time. So the core question about computational power boils down to, is BPP really just a subset of BQP?
Exactly. Are there problems that a quantum computer can crack in polynomial time with a good chance of getting it right that no classical computer, even with randomness, could ever solve efficiently? That's a huge question that drives a lot of research in quantum computing and has huge implications for what we think is computationally possible.
Now, this Church-Turing thesis, it wasn't just some abstract idea, right? It evolved into what we call the physical Church-Turing thesis.
Right. It takes that idea and applies it to the physical world. It says any physical process can be simulated to any degree of accuracy by a universal Turing machine.
Yeah.
And the complexity of a physical process, how hard it is to simulate, actually has real physical meaning. It's like saying the difficulty of simulating something is fundamentally connected to how computationally demanding it is.
And then we have people like Wolfram saying a universal Turing machine can simulate any physical system, and Aharonov taking it even further, saying a probabilistic Turing machine can simulate any reasonable physical device with only a polynomial overhead and resources.
Exactly. But to make this physical thesis really work, we need to connect real-world resources, like space and time, to computational ones, like memory and the number of steps. There are different ways to do this, and they lead to different versions of the physical Church-Turing thesis. And for a philosopher, it's important to keep in mind that the original Church-Turing thesis about what we can calculate in an abstract sense is different from its physical counterpart. The original is about logic and proof, while the physical one is about the power of the physical universe itself.
Which leads us to all these shortcuts to computation that people have explored. DNA computing, analog computation, things like that. There was a lot of excitement thinking maybe they could get around those complexity barriers by using different physical mechanisms.
There was. DNA computing, for example, it used the idea of massive parallelism in molecular interactions to try and solve NP-complete problems quickly. But when you look closer, it turned out you still needed a ton of DNA molecules, a resource that still grew exponentially with the problem size. Similarly, analog computation, it seemed to offer instantaneous solutions, but then you ran into physical limits that slowed things down exponentially. So it seems like these classical physical models haven't really broken the physical Church-Turing thesis when it comes to complexity. They always hit a wall where some physical resource you need grows exponentially with the problem.
But then quantum physics entered the picture. The big question became, could we harness the strangeness of quantum mechanics to find shortcuts that classical physics just doesn't allow? And the pursuit of the quantum computer began with a hopeful yes.
Absolutely. Now, we look at the early history of quantum information processing. There were some hints of these ideas floating around, but the first formal academic work really started popping up in the 70s and early 80s with researchers like Holevo, Poplavsky, Ingarden, and Manin. They were looking into how much information you could cram into quantum systems.
But the real pioneers, the names we still talk about today, are Bennett, Benioff, Deutsch, and of course Feynman in the early 80s. Their work on the fundamental limits of computation was crucial.
It was. As technology was shrinking and shrinking, they realized that at the atomic level, the rules of the game are quantum. So the question naturally arose, could we build a computer that plays by those quantum rules? Feynman, in particular, he was one of the first to propose a model back in 1982, showing how quantum systems could actually compute. And he famously said that simulating quantum stuff with classical computers would be a nightmare, way too computationally expensive.
And then in 1985, David Deutsch proposed the first universal quantum Turing machine. That was a huge step towards the quantum circuit model that we talk about today.
It was. And the 1990s were a time of incredible progress. We got the Deutsch-Jozsa algorithm in 1992, then Simon's algorithm in 1994. Simon's work was really important. It laid the groundwork for Peter Shor's groundbreaking factoring algorithm, also in 1994. That was a huge moment. It got people excited way beyond physics because of what it could mean for cryptography, for cybersecurity. Suddenly, the idea of quantum computers went from a theoretical curiosity to something that could change the world.
And the experimental side wasn't too far behind. Proposals for and even implementations of basic quantum gates, like the controlled not CNOT gate, were appearing in the mid-90s. And both Shor and Andrew Steen, they independently came up with the first schemes for quantum error correction, a crucial step towards building practical quantum computers. And we can't forget Lovegrover's search algorithm in 1996, which showed a provable speedup over classical search algorithms, even if it wasn't exponential.
And the field has just kept evolving. We saw NMR-based quantum computation, adiabatic quantum computing, and the cluster state model popping up in the early 2000s. More recently, we've entered the era of NISQ, noisy intermediate-scale quantum computing. These devices have a limited number of qubits, and there's still a lot of noise, but they're getting better. There have even been claims of quantum computational supremacy, where quantum computers have supposedly done things no classical computer could dream of, though those claims are still being investigated. But even with all this progress, the big questions are still there. Can quantum algorithms really solve intractable problems efficiently? And can we actually build the large-scale, fault-tolerant quantum computers we need to run them?
It's quite a story. So let's move on to what I think is the real mystery at the heart of all of this. Quantum advantage. What is it about quantum computers that gives them this potential power? What's fundamentally different compared to classical computers that could lead to such dramatic speedups?
That's a question that everyone is asking, and there's still a lot of debate. There isn't one single answer everyone agrees on. To even try and answer it, we need to look at the building blocks of quantum computation. The basic unit of information is the qubit. It's like the quantum version of a bit.
Right. A classical bit is simple. It's a 0 or a 1. But a qubit, it's in a superposition. It's both 0 and 1 at the same time. And we often visualize this using the Bloch sphere. I think for a philosopher, that's a nice way to think about all the possible states a qubit can be in.
Exactly. Mathematically, a qubit state is alpha Silbert 0 wrangle plus beta 1 wrangle, where alpha and beta are complex numbers that satisfy a certain rule. The magnitude squared of these numbers tell you the probability of measuring the qubit as a 0 or a 1. But because alpha and beta can be any values within that rule, you might think, wow, a single qubit can hold infinite information. But here's the catch. When you actually measure a qubit, you only ever get a 0 or a 1. The act of measuring forces it to choose.
So it's not about storing infinite information that we can directly access, but there's this idea of specification information versus accessible information. What does that mean in the context of a qubit?
So the accessible information is what you can reliably get out of a qubit by measuring it. That's at most one bit, a 0 or a 1. But the specification information is all that richness hidden in the superposition before you measure it. It's all those complex amplitudes, those alpha and beta values that describe the qubit state. Think of it like this. You have this incredibly detailed blueprint of the qubit state, but when you look at it, you only see a simplified 0 or 1. And the power of quantum computing, it's thought to come from our ability to manipulate that hidden blueprint, that specification information, using quantum gates, which are these special operations that act on superpositions, before we finally do a measurement.
So we have these qubits and these probabilistic superpositions, and then we have quantum gates, which are like logic gates, but for these superpositions. And you mentioned they're unitary, which means they're reversible.
That's right. Quantum gates are mathematically represented by matrices called unitary matrices, and you can think of them as rotating the qubit state on that Bloch sphere. Unlike some classical gates, like A and D or R, all quantum gates are inherently reversible. That reversibility is a fundamental part of quantum mechanics, and it really impacts how quantum computations are structured. We figured out that a small set of 1 and 2 qubit gates, like the CNOT gate, are universal. That means you can combine them to approximate any quantum operation you want on multiple qubits.
And just like classical logic gates are connected to form circuits, these qubits and quantum gates are linked together to form quantum circuits. You typically start with the input qubits in a well-defined state, like all SUA days, and then you get the output by measuring the final state of the qubits.
Exactly. Those early quantum algorithms, like Deutsch-Jozsa, Simons, Shor's, and Grover's, they were all developed within this quantum circuit model. And it's worth pointing out that while there are other models of quantum computation, like adiabatic quantum computing and measurement-based quantum computing, like the cluster state model, they've all been shown to be computationally equivalent to the circuit model. They might need a bit more resources, but not exponentially more. And it's interesting we see a similar kind of computational equivalence among different classical models of computation.
Now, how do quantum computers simulate classical computation? Because if they're supposed to be a more general type of computer, they should be able to do at least what classical computers can do, right?
Absolutely. Quantum circuits are always reversible because of the unitary nature of quantum gates. But classical circuits often use irreversible gates. So, to simulate deterministic classical computation on a quantum computer, we usually use something called the Toffoli gate. It's a reversible classical gate that has a quantum version. This lets a quantum computer perform any classical logic operation, though it might take more steps than a dedicated classical circuit. And for simulating probabilistic classical computation, the Hadamard gate is key. It can take a qubit in a definite state, like 0, and put it in a superposition of 0 and 1. When you measure it, you get 0, 1 with equal probability, like flipping a quantum coin.
So quantum computers can, in principle, do everything classical computers can do, though maybe not always in the same way. But the big question is, what's the source of that potential power, that speed up that everyone is so excited about?
This is where the philosophical debates get really interesting. Absolutely. And there are lots of ideas out there. Some people point to quantum interference. That's how different quantum computational paths can either reinforce or cancel each other out, making it more likely to get the answer you want. Others focus on entanglement, the spooky action at a distance that can link multiple quantum systems. But there are arguments saying entanglement on its own might not be enough for a computational advantage. And then there's contextuality, the idea that the result of a measurement can depend on what other measurements you do at the same time. That's been proposed as a potential resource too.
And then there are people like Jeffrey Bubb who look at the logical structure of quantum mechanics itself, saying its unique features are what allow for these speedups. And Christopher Duell, who's made a strong argument for quantum parallelism. And of course, there's David Deutsch and his connection to the many worlds interpretation of quantum mechanics. There's a whole lot to unpack here.
There really is. Let's dig a little deeper into quantum parallelism and the many worlds interpretation, MWI, as a possible explanation. The idea of quantum parallelism comes from the fact that in some quantum algorithms, it seems like you're evaluating a function for many different inputs at the same time, thanks to superposition. Duell calls this the quantum parallelism thesis, QPT. And Deutsch famously argues that the best way to explain this apparent parallel computation is through the MWI. The idea is that the quantum computer, being in a superposition, actually exists in multiple universes, with each universe handling a different part of the computation.
But not everyone buys into this, right? People like Itamar Potowsky and Andrew Steen have raised some concerns about what we actually get out of these computations. After all, when you measure the final state, you only get one result. And sometimes the probability of getting the right answer might not be that much higher than with a classical approach.
Right. Potowsky's point is that real quantum speedup requires creating clever superpositions that make it much more likely to measure the right answer, not just exploring a huge number of possibilities in parallel. And Steen goes even further. He suggests that quantum algorithms might actually take fewer computational steps than their classical counterparts, but those steps are much more cleverly arranged. He thinks the QPT might be based on a slightly misleading way of looking at the quantum formalism.
And Duell, while he agrees that there's something real about this parallelism described by the QPT, he argues that it doesn't necessarily mean the MWI is the right interpretation. He points out that the crucial phase relations between different parts of the superposition, the things that make quantum interference and speedups possible, are global properties of the whole quantum state. They're not just a bunch of independent computations happening in separate universes.
Exactly. He says this interconnectedness, the global nature of those phase relations, means the QPT doesn't really favor the MWI over other interpretations of quantum mechanics. Meanwhile, proponents of the MWI, like Hilary Greaves and David Wallace, argue that the information from those parallel computations could, at least in principle, be accessed, maybe with more advanced measurement techniques than we have now. They also say the MWI is a strong contender because it helps explain other foundational issues in quantum mechanics, like the measurement problem. It gives a coherent picture of quantum reality.
And Scott Aronson and Sean Cafaro have pointed out this interesting tension. How compatible is the many worlds explanation of quantum computing with the standard MWI based on decoherence? Quantum algorithms rely on maintaining these coherent superpositions for a long time. But for distinct worlds to emerge in the MWI, you need decoherence, which is the loss of that coherence, through interaction with the environment. Cafaro questions whether the criteria for identifying these computational worlds in the MWI are really justified, and if they fit with the standard decoherence story. He also asks if the MWX can even work with measurement-based models of quantum computation.
It's a good question, because even if we tweak the way we define worlds in the context of computation, it's not clear how you'd get those stable, independent worlds like the MWX describes in measurement-based computation. In that model, you're doing a sequence of measurements on an entangled state. It's a very different picture.
So it seems like the root of quantum speedup is still a bit of a mystery, even if we put aside the really radical interpretations like the MWI. Figuring out exactly what quantum resource or mechanism is responsible for the potential advantage is still a big open question.
Definitely. It makes us rethink some basic questions about how we even define and measure the complexity of a quantum algorithm and what kinds of operations we can realistically do with actual hardware. It seems like the power doesn't come simply from the way the quantum state evolves in time, according to the Schrödinger equation, because in some sense, you can simulate a quantum system with a limited number of states on a classical computer in polynomial time.
So it's not just about the quantum system changing over time, but about how you set up the initial state and what operations you do to create a final state that encodes the answer to your problem. And you need to be able to extract that answer through measurement. It's about creating those clever superpositions that Potowsky talked about.
Exactly. The reason why some quantum computations are so hard to simulate classically is that figuring out the important parts of those clever quantum states takes exponential resources. If we're talking about the quantum circuit model, we probably need to think about how many local 1 and 2 qubit operations it takes to create those special superpositions. The trick, and where the quantum advantage seems to lie, is doing that in a number of steps that only grows polynomially with the problem size.
Okay, we've gone through some seriously complex stuff. Let's shift gears and talk about the philosophical implications of quantum computing. This is where it gets really relevant for a philosophical audience.
It does. The development of quantum computing has already sparked a lot of discussion and rethinking in the foundations of quantum mechanics. Some philosophers and physicists even say that the success and potential of quantum computing might change how we view the measurement problem, one of the biggest mysteries in quantum mechanics. Maybe it doesn't need a traditional solution after all.
And this ties into the growing interest in informational approaches to quantum mechanics, right? The idea that information is much more fundamental in quantum mechanics than in classical physics. Some people even say it should be a core principle of the theory.
Right. In these informational frameworks, measuring something is mostly seen as gaining information about the quantum system. And some argue that interpreting a measurement outcome as information requires thinking of the observer as an information processing system. From this perspective, classical physics is like a special case where how you represent the observer doesn't really change the information you get. Quantum mechanics is more general. It can represent correlations between systems, including observers, that go beyond what's possible classically. This might make people less worried about finding some deeper theory that explains the measurement problem in a way that fits our classical intuitions about definite outcomes.
But not everyone working on quantum foundations buys into these informational interpretations. Some are holding out hope that building large, well-controlled quantum computers might give us an empirical way to tackle the measurement problem, particularly in relation to collapse theories.
That's true. Collapse theories try to modify the standard Schrödinger equation. They say that quantum superpositions spontaneously collapse under certain conditions, especially when decoherence, the loss of quantum coherence due to interacting with the environment, is suppressed. Building a large quantum computer means having extremely good control over the quantum system and suppressing decoherence. So it's possible that as quantum computing technology gets better, we might be able to test the predictions of different collapse theories against the effects of decoherence. If we build a quantum computer with the right architecture, it could give us empirical insights into this fundamental problem. It's like a kind of experimental metaphysics, as the philosopher of science Abner Shimoni called similar developments in the past, where new technologies let us test basic physical assumptions. But it's important to remember that the specific design and operation of the quantum computer would be crucial for drawing any metaphysical conclusions, since different collapse theories predict different kinds of collapses under different conditions.
Moving beyond the interpretation of quantum mechanics itself, it seems like quantum computing also has some big implications for how we understand causality, especially in the quantum realm.
It does. There's been a long and complicated debate about whether quantum mechanics and our usual ideas about cause and effect, especially local causality, can even coexist, especially after Bell's theorem. But inspired by ideas from computer science, some researchers are looking at the possibility of explaining quantum phenomena using local causality within an interventionist framework. They use the mathematical language of quantum channels to model quantum events as processes with well-defined inputs and outputs. This approach is interesting because it might allow us to create causal models for quantum phenomena that don't need non-local influences and that meet other criteria for a good causal model.
And then there's this view put forward by Sean Cafaro and others who say quantum computation and information theory are practical sciences, not branches of fundamental theoretical science like traditional physics. What does that distinction mean for how we understand the field?
The key difference is in the goals and methods. Traditional theoretical physics wants to understand the fundamental nature of reality, regardless of any specific application. But practical sciences, like quantum computation and information theory, they're all about how you can control and engineer physical systems to do specific things, like compute or transmit information reliably. Recognizing this difference can help us avoid conceptual confusion when we try to interpret what quantum computers can do or evaluate how important classical simulations of quantum phenomena are for addressing fundamental questions in physics. Some no-go theorems, which are crucial for understanding the limits of physical theories, might not be so relevant for figuring out what efficiently simulable quantum phenomena can and can't do from a computational perspective.
And this brings us back to the Church-Turing thesis and David Deutsch's argument that it implicitly assumes a fundamental principle about physics, which he calls Deutsch's principle.
Right. Deutsch says that the Church-Turing thesis implicitly assumes that any physical system you can actually build can be perfectly simulated by a universal computer operating with finite resources. He argues that this principle doesn't hold in a classical world because classical states and dynamics are continuous. But he thinks it's true for quantum physics because there's a universal quantum Turing machine or a universal quantum circuit. But other people, like Peter Timson, disagree. They say the Church-Turing thesis is ultimately about the mathematical idea of an effective method of computation, and it doesn't need to be based on physical principles to be meaningful or true.
Quantum computation also seems to shed light on the distinction philosophers of science make between how actually explanations and how possibly explanations.
It does. Sean Cafaro argues that when we try to figure out where the quantum speedup for a specific problem comes from, we're basically comparing different algorithms and looking at the abstract spaces of possibilities they represent. By answering the how possibly question, how one computational process can, in principle, beat another, we might find that digging into the detailed how actually of the underlying quantum physics doesn't really tell us that much more about the computational advantage itself at a certain level of abstraction.
Lastly, let's talk about computational kinds and how quantum computing might impact the philosophy of mind, especially the debate about the autonomy of computational theories and functionalism.
This is a really thought-provoking area. In weak artificial intelligence and functionalism, there's been a lot of focus on machine-independent computational properties, or kinds. The idea is that you can define a computation abstractly without worrying about the specific physical hardware that's running it. But if quantum computers can efficiently solve problems that are impossible for any classical computer, as suggested by work like Bernstein and Vazirani's, who redefined computational complexity to include quantum computing, then fundamental concepts like efficient algorithm or complexity classes like NP might become dependent on the specific machine. In their analysis, you have to consider the physical substrate, the quantum nature of the computer. This could challenge the traditional functionalist view that computational types and properties are purely abstract and not tied to physics. It might even be a counterexample to some arguments against reductionism in the philosophy of mind. It suggests that at least some computational properties are fundamentally linked to the underlying physical mechanisms. But as philosopher William Seeger has pointed out, there would still be big conceptual challenges to a fully physicalist account of consciousness and mental states, even with the unique computational powers of quantum computers.
Wow, that was quite a deep dive. We've gone from the basics of computability to some incredibly profound and challenging philosophical questions raised by quantum computing.
We have, and it really shows how intertwined computer science, physics, and philosophy are in this cutting-edge area of research.
And as we've seen, even with all the theoretical breakthroughs and experimental progress, there is still a lot of theoretical and practical challenges in building large-scale, fully functional quantum computers. And the philosophical questions, as we just discussed, are far from settled.
Absolutely. The very nature of quantum advantage, its origins, and what it ultimately means for our understanding of computation, the physical world, and even explanation itself are still open for debate and philosophical exploration. Especially for someone with your background in philosophy, there's a lot to think about here.
So here's a final thought to chew on. What if problems we thought were fundamentally impossible to solve efficiently become solvable with quantum computers? How would that radical shift in our understanding of computational limits change how we understand the very limits of knowledge and the nature of the physical world?
It's a question worth pondering. And we encourage you, our listeners, to explore the Stanford Encyclopedia of Philosophy entry on quantum computing and all the other great work out there on this topic. Think about which explanations for quantum speedup make the most sense to you and, maybe even more importantly, why those explanations resonate with your philosophical intuitions.
Thanks for joining us on this deep dive. Until next time, keep those philosophical gears turning.